Welcome to this video, learners. In this video, I'm gonna talk about when not to use Pearson's correlation coefficient. This is an interview question recently asked in one of the machine learning interviews as well as AI engineer roles. So everyone learns about correlation coefficient. Okay, I'll talk about it first and then I'll talk about when not to use it. So it's so popular that this coefficient has to be high, greater than 1, then your dependent features and independent features are highly correlated, and that's when you are going to use this features in the linear regression model. That is the fundamental definition for Pearson's correlation coefficient. And we know that it also establishes the relationship between two variables, and it varies between minus to 1 to 1. And for example, if we take a distance versus price example, a scatter plot, in the case of simple linear regression, we generally look at the correlation coefficient of how distance is increasing, and if distance is increasing, how price is changing. And we also know the formula for it. It's nothing but x minus x bar, y minus y bar divided by this corresponds to standard deviation of x, and this corresponds to standard deviation of y. So that's the correlation coefficient between any two variables. And typically we do this a lot of with regression. So for example, we have price as our regression variable or y variable. We are going to check, hey, how is the distance? Let's say if there is another variable, how is the traffic? And we are going to correlate them using PD dot correlation in pandas, and we generally check the correlation coefficient. If it is greater than 0.5, then you consider it a strong correlation. Now, there are many problems to Pearson's correlation coefficient, which are the edge cases which people don't study a lot. So that's why I thought I will cover that in this particular video. So when does it fail? Is the first reason is outliers. In fact, I have taken a small linear data with distance and price, and I've calculated Pearson's correlation coefficient. And I've also did a scatter plot so that you understand it. If you look at it, the data is perfectly linear with a little bit of noise. And if you see, the Pearson's correlation is 0.998, Spearman is also 0.998. Oh, by the way, Spearman is an the alternate to Pearson's correlation coefficient, and I'm gonna introduce it in a while. Now, I've took in the second case an outlier. This outlier is a 50 kilometers distance, but the price was given as just 10 units. Probably a discounted one, or probably data entry issue, probably a software glitch. It could be anything, right? But as soon as you have an extreme point, you look at your Pearson's correlation coefficient, it dropped to almost 0.114. If you just drop this and use the original data, the coefficient is 0.99. And from 0.99, the effect came to 0.11, which is a very drastic change. So I took this example intentionally to highlight it, whereas your Spearman is still high, 0.726. So lot of times in real life, we kind of get outliers, and without removing outliers, if you look at correlation coefficient, you will be confused, or you will be typically fooled also. So this is one big problem. Having outliers will affect your Pearson's correlation coefficient, but it doesn't affect Spearman's correlation coefficient. So we will talk about that case. And one more case is nonlinearity case. In general, you learn that, hey, we will use Pearson's in the case of linear regression. But can you guarantee that our data always is linear? Or can you guarantee that, hey, my price versus distance is linear? No, you cannot guarantee that. Because real life datasets come with their own problem statements. You cannot dictate a linear relationship upfront. So here I took another example, trip distance versus trip price. If you clearly observe, okay, the relationship is not linear. It is increasing, but that increment is getting saturated if you notice. So when you look at this kind of correlation coefficients, you still get 0.88, whereas Spearman says 0.986. So what is the difference here? Pearson's is showing slightly lower relationship. Spearman is still showing high relationship. What does this mean is there is a non-linearity here. That non-linearity is leading to high difference between Pearson's and Spearman. Let's talk about it. So in this video, I'm going to discuss, hey, how do you calculate Spearman? And after calculating it, I'll talk about how it helps in detecting nonlinear cases. It helps in detecting outlier cases also. So this Spearman correlation is designed to find out monotonicity. Okay, what is monotonicity is it measures the increase, whether it is increasing or not. It doesn't measure every time is it increasing by same unit or not. Okay, so if you take an example x and y, if x is 1 and y is 1, then x becomes 2, so y also becomes 2. So increased by 1 unit and y also expected to increase by 1 unit. That's when Pearson's correlation is 1. And x increases by 1 more, then y also expected to increase by 1 more. X increases by 1 more and y also expected to increase by 1 more. Only then you consider this as a r equal to 1, which is Pearson's correlation value of highest possible value. That means x is increasing by 1 unit, y is increasing also by 1 unit. But Spearman is not looking at that. Spearman doesn't worry about how much increase is there. So x and y are there. Let's assume x is 1, y is 1.5. Okay, and x becomes 2. Even if y becomes 1.7, that is fine. X becomes 3, y still is 1.8, that's fine. X becomes 4, y is just 1.9, still fine. Okay, you still call it as r equal to, here you call it as rho equal to 1. Rho is basically Spearman's. So it doesn't matter, hey, are you increasing or not? That's what matters. By how much I am increasing doesn't matter. 1.5 to 1.2, 1.7, 0.2 increase. Here again 0.1 increase only. By the way, if it is 1.81 also, if it is 1.81 also, still your rho is equal to 1. Okay, if it is 1.92 also, still rho equal to 1. If it is 2.8, still rho equal to 1. If it is 2.9, still rho equal to 1. You don't care about how much it is increasing when you are doing Spearmans. You only care whether increased or not. But the caveat here is, you may say, Prithvi, how do I recognize? For example, if it is 2.9, let's say here, at 4, it is 2.9. Now at 5, you have to be definitely greater than 2.9. Let's say it is 2.6, for example. Then this row will get affected. Because 4 to 5 increase is there, but 2.9 to 2.6 decrease is there. So that's what your Spearman's coefficient is detecting. Is if x increases, does y increase or not? That's what it all bothers. Whereas Pearson, if x increases by 1 unit, y should also increase by 1 unit. That's what your Pearson's measures. Okay, so we will take a small example and see how Spearman's is calculated, and based on that we will take it further. So I'll take an student example. Let's say student, their math score and their science score. I'm interested in correlation between both of them. Student 1, 2, 3, 4 and 5. Okay, imagine math score as, for the sake of ease, 70, 80, 90, 95 and let's say 98. Increasing order, I took it for the sake of ease. Okay, here I'll take it 60. Then let me increase it to 55, decrease it to 55, then again 70, 75, then let's say 80. Got it? Now, in Spearman's, the most important thing is rank. We are going to calculate rank of math and rank of science for each student. As you know, rank is basically whoever gets the highest marks, you'll put it as 1. Or whoever gets the lowest mark, you will put it as 1. Either way is fine, but please maintain the same rank or same measure in both cases. So in this case, I'm taking rank highest rank as 1. So 98 is the highest for math, then second, then 90 is the third, 80 is fourth, 70 is fifth. Okay, highest is the first rank. So that's what I get. So you should keep the signs also same there. Highest is the first rank. So where is the highest? Again, 80 is the first. Well and good. Then 75 is second rank. Okay, 70 is the third rank. Okay, now fourth rank is 60, fifth rank is 55. So just interchange of your ranks here. Now you are going to calculate D. D is going to be difference of the ranks between the same. So difference of rank is 0, 0, 0, 4 minus 5, this is minus 1, 5 minus 4, this is 1. And from here you calculate D square. D square is going to be 1, 1, 0, 0, 0. And from this you are going to calculate rho. 1 minus 6 into D square, sigma of D square. So 1 plus 1, 2. 6 into 2 divided by n, number of digits, number of rows here. So we have 5 rows, it's going to be 5 into 5 square 25 minus 1 24. So 1 minus 12 by 4 5 0 2 5 to the 10 12 1. So 12 1 by 10, this is 0.1, which is 0.9. So Spearman's correlation coefficient rho is going to be 0.9 in this particular situation. Now imagine for that simple example that, hey, this is also 4 and this is also 5. For the sake of it, I'm just changing it, 5 and 4. In that case, your d's will become 0. Both d square also becomes 0. So this entire side becomes 0. So that means rho is equal to 1. Highest possible rho value. Now, as long as you can keep the rank same, right, the science score can keep the same also. So if, for example, here, I'm adjusting accordingly. So rank of science also should be 5, right? So let me take lowest score 55 here and 60 here. Now rho is equal to 1 because rank is 55 is 1. Now imagine the score changes to 54 here. Still your rho is same. Score changes to 24 here. Still your rho is same, 1. But imagine Pearson's will change the correlation coefficient if you change, because that changes the mean, that changes the correlation coefficient. So Spearman is only worried about, hey, this increase, this increase, this increase, this increase. How much doesn't care, right? So that's why you got the concept of ranks here. And let me tell you, this is very important in certain cases. For example, when relationship is monotonic but not linear. The best example of monotonic relation is this one. Hey, you have seen the increase, but the increase is not consistent. Every time increase need not be 1. Okay, from here to here increase is high, here to here increase is high, but after a certain point increase is low. This is how Uber also does it, because if you keep on giving more kilometers, okay, then they have to saturate that curve, right? So that bulk discounting comes into picture. It may not be exactly like this, but it is almost close to this one. At lower this, so this is clearly non-linear relationship, okay, but monotonic. Monotonic means continuously increasing, but not by same units. Okay, if x increases, y increases, but not by same unit. So that's what monotonic is. To maintain, to measure that monotonic relation, we use Spearman's correlation coefficient. Now, when data contains outliers also, this is really helpful. And finally, when variables are ordinal, that means order very specifically, you go and take survey ranking. Okay, there's one variable which is just giving you rank or rating. Okay, you look at ratings of two movies, right? Two person, for example, person one is rating certain movies, person two is also rating certain movies. Now, how do you calculate similarity between person 1 and person 2? Because ratings are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If you calculate correlation coefficient, Pearson's, it will not be good. But if you calculate Spearman's, it will be good. Survey responses marked as 1, 2, 3, 4, 5, 1 to 10. Again, it will be good. Any variables, any two variables when they are ordinal, if you look at Spearman's correlation coefficient, it will give you much better metric than Pearson's correlation coefficient. So I hope in your next interview, whenever someone asks you, hey, where does Pearson fail or where is Spearman's used, you can conclude this. Thanks so much for watching.